Hello guys, so we're here again to discuss the continuation of the limit analysis in slabs. So for this particular lecture, I would like to give you the other method for limit analysis in slab, uh, which is the strip method. So just a review of the previous method, we actually have discussed the yield line theory or analysis, which is actually an upper bound approach. Uh, Yield analysis. Where the computed load is always greater than expected or actual. So we are talking about load capacities beyond the estimate. Okay, so for the strip method now, we will be talking about the lower bound approach, which is um, made to consider that the computed capacity or computed load driver is greater than, so it's less than or equal to the actual load. So perhaps we can deduce from this that the strip method is uh, rather conservative method, while the YLA or the yield line analysis is a rather less conservative approach. Not to mention the advantage of one over the other in terms of applicability. So to define to you again the lower bound theorem, simply states that the load computability is the machine a statically admissible set of interval forces would always be smaller or less than or equal to the correct elapsed load. Okay? So we also have to take note that the strip method is a static method, so it's a static method which can be done using analytics and graphical solutions. When we are analytical yeah. And the advantage of such, aside from being conservative, is that uh, we are dealing here with a design procedure. Okay? In the yield line analysis, the procedure is investigated. Okay? In the yield line analysis, you have to take note that this is more investigative, trial and error procedure. While in the strip method, we are actually doing a design procedure wherein the moments, the design moments are computed on the basis of model. Okay, your slab panel into strips. Okay, that's why it's called a strip method. So the model is done by creating uh, the strip type of okay of a slab, okay, and then putting the statical equivalence of the moment uh, based on the boundary conditions, the supports, and the loadings. Not to mention the presence of poles and concentrated loads, as I will be discussing today. So for your uh, capacity versus curvature relationship, okay, we can make this in terms of load capacities versus deformation in terms of curvature or rotation. The shape of the curve is actually almost straight up to the yield, okay, capacity, and suddenly drops into a flat, flatter curve into the grade, okay. So the lower bound is actually at this point and the upper bound is at this point, and we are expected the actual collapse load or capacity is in between. So in here, the upper bound YLA is more favoring this ultimate capacity greater than the collapse load, and here the strip method is uh, more favoring the yield capacity which is less than the collapse load. So this design method now of strip analysis by which required reinforcement can be determined is more, as I told you a while ago, a design procedure. So the distribution of the reinforcement will be varied for different sections as compared to the yield line method where reinforcement are normally uniform throughout the entire sections. Easier to use on slab with irregular boundaries. Okay? Boundaries. So when we talk of boundaries here, we're talking of not only the shape but also the support or boundary shapes. So the basic principles and the governing equation is actually given by this differential equation, which serves as our basis to physical, uh, uh, rather the analytical representation of the physical behavior of slabs used in finite element procedure. Okay? So this is exactly the same formula that the strip method is following, provided that uh, in here a lot of assumptions are made to simplify the finite element solution. So strip method is more or less a simplification of what the FEM method is all about. And neglecting torsion, we ignore the moment xy, which is more or less only an assumption, but rather very uh, acceptable since we know that torsion and shear distribution cancels each other uh, when we're talking of slab behavior. Okay, so the reason for that is because slab has boundaries in two directions, therefore uh, the torsional requirement is normally counteracted by the shear capacities due to redistribution. Okay, so since it is simplified in that regard, then this equation will now be uh, made much simpler into this equation. Wherein, we assume that further that the load resistance is now divided only in two orthogonal directions, known as the beam strips, and they are independent of each other for as long as we satisfy equilibrium static condition uh, in these two orthogonal directions, then we will have no problems regarding safety. So in the x direction, we can assume that the load that is resisted is in terms of k, which is the remaining load requirement will be resisted in the other direction by 1 minus k. Of course, the negative sign here simply indicates that your positive direction for loads is y is up. Okay? So the range upon which your load will be distributed in terms of k is from 0 to 1. And the choice of load distribution now may be determined through these assumptions and criteria that will serve as a guide for all of us in such conduct of strict method procedure. So first, any value of k may be used, resulting in a different distribution of load or speed. If we want to distribute it entirely in one direction alone, then we will be having a one-way action. If k is 0 and 1 minus k is 1, or k equals 1 and 1 minus k is 0, then we're talking here of simply a one-way action. Of course, a one-way action has some criteria to be satisfied based on different principle that I'll use. An example of that are the ACI uh, methods that we have discussed previously. So for number two criteria, practically arbitrarily choosing a value of k, the distribution may be inappropriate, causing excessive cracking or deflection at the service load level. So note that the strength requirement is satisfied but not serviceability. Okay. Cracking is a serviceability issue. It doesn't mean that when a slab cracks, especially slab cracks, then failure is imminent. So, but of course, serviceability wise, it's not uh, acceptable. But still, we can say that the strength requirements still satisfied, and we only have to deal with our experience and some guiding principles for us to be able to choose a value of k in order to avoid uh, intense cracking. So in general, the knowledge of the general distribution of elastic moment should guide the choice of the distribution. So still, uh, the basis of our nonlinear response and inelastic approach or plastic uh, uh, approach in terms of analysis and design will still be founded on our knowledge on elastic principle. Okay, so if you are not familiar with elastic behavior, then it's really very uh, irrational. No? It's very irrational for you to be able to capture the uh, appropriate choice of your k value in this particular method. So the choice of the load distribution, for example, for a square slab may be 50% in each direction over the entire slab. Okay? Hence, if we are going to make use of a an elastic analysis on the moment, the bending moment, we can say that this is simply simply supported beam with uh, load in each direction equivalent to 50% of the total weight on the entire slab. Okay, hence your maximum moment if you want to design the slab at the critical section is simply a one half of your static moment for the whole load W, hence Mmax is WL squared over 8 over 2 or simply WL squared over 16. So note that with K equals 0.5, the resulting uniform distribution of moment, reinforcement across the grid in both directions will create some problems on serviceability manifested by cracking at certain sections of your slab. By using a tributary area, then the load path nearest to the support will be your choice of distribution. Hence, if we are uh, considering this square slab with a 45-degree distribution by means of the tributary area, um, then if I cut a section A at this particular location at y distance from the origin, I can now graph the lateral load distribution in this direction. Okay, so if we're looking here as this is the longitudinal distribution, this is the long direction, this is the transverse direction or lateral direction, then my load here using this strip, this particular strip at y at y equals or at this height equals y, then this is your loaded strip in this direction, because this will be carried by this beam here. Then supports here will carry this up to this point as your longitudinal distribution of moment. Hence, I have here a partial uh, uniform load at a distance equivalent to y distance. Since this is a 45-degree, if this is a square slab, then this is simply maximum moment is simply a cantilever moment with a load equivalent to y extended at a distance of w extended at a distance of y. So this is wy squared all over. At this section, the distribution now of your loading will be a varying, a linearly varying, a parabolically varying load starting from 0 here going to a maximum, or sorry, linearly varying load from 0 to a maximum. So this is now your lateral load distribution uh, in terms of the bending moment. So already the bending moment, if we are going to look at the load here, this is simply supported in that direction. So this will create 0 at this one, 1 up to this one. Okay, so this is your loading that will create your maximum bending moment WL squared all over it. Okay, so take note that the design moment is continuously varying, therefore the reinforcement is also varying. So in this case, in this at this particular direction, we have no problems, since we can assume that all the reinforcement of this direction can actually carry wy squared over 2, but in the lateral distribution of the reinforcement here, then starting from a 0 requirement up to a maximum requirement here, it is not practical to make a continuously varying reinforcement layout. Okay, although this is more exact, in practicality, especially in actual implementation, is rather not advanced or recommended. So because of that, we ought to recommend that we divide the slab into segments. That's why the strip method, uh, this method is particularly tagged as a strip-based approach, since dividing it into segments will give you the possibility of satisfying the variable, no, moment requirement, but at the same time making it practical to implement in construction, since by segment we can now introduce a fixed spacing or a uniform spacing on that particular strip. So in this case, the division suggested is simply of L over 4 distance from the opposite supports, making your midspan strip or the middle strip equivalent to L over 4. So in these two directions, therefore, the uh, moment, okay, or variation will then be equivalent to this based on this loading in this direction. So if we call this the x direction, and this based on this loading in this direction. So this is one. Okay, so why is it that there is a difference uh, a moment diagram for this direction here, no? If we are to look on on this particular slab, this square slab, okay, this is square slab. The lateral distribution of moment at the middle strip, okay, so we're talking here at the middle strip, is considered here, okay. So if this is the middle strip that I'm talking about, and this is the longitudinal strip at the middle strip, it's the long strip, okay. So we take note that in the longitudinal strip here, we are talking of the middle strip, which is defined in terms of this. So you will notice that I have here a full load W, because this is only directed in one direction, full load, and this is 50-50 since this is square, 50%, and then a full load there. My moment diagram will simply be parabolic, but since this is not a uniform load, then a slight decrease in the slope here will be obvious. Okay, and if we're going to make use of a particular solution on how to get the moment maximum here, so since this is 5 WL squared over 64 using, of course, elastic methods. Now the edge strip, notice that at the edge strip there is no along this direction distribution here, so this is 0 at the middle part here, and this is W over 2 since this is distributed two-way. A 50-50 distribution is expected for square slab here. So this is W over 2 and W over 2. Again, the way on how to get the maximum moment for a simply supported beam with a partial load, if the distance here is known, Okay, then uh, if this is L over 4, so this is simply equal to W over 2 times L over 4 squared all over 2. Okay, so it's simply a cantilever, just like a W uh, prime x squared over 2. Okay, well, W prime is this one, your x is L over 4, and this 2 is a constant. It's a cantilever moment arm. Okay, so this becomes now 16 times 2, 32 times 2, this becomes 64.